Okay, let's do the sample final. So the following is based on a table of values of the position in meters and the time in seconds, and the average velocity between 0.25 and 1.5 would be 14.13 minus 6.55 over 1.5 minus 0.25, and that works out to be 14.13 minus 6.55 divided by, see, that's 1.25, 6.064 meters velocity per second. This is change in the position, this is change in time. Determine the slope at 1.5 using the central difference. So I'm going to go 19.58 minus 10.36 over 1.75 minus 1.25. So I get 19.58 minus 10.36 divided by 0.5, and I get 18.44 meters per second. So now we're going to do a linear approximation, which is, we're going to do it as the closest place to 1.47 we have, which is 1.5. And so the slope will be what we got in this one, the slope at 1.5. So it's going to be 18.44 times x minus a plus the y value at 1.5, which was 14.13. And then we're going to find the answer to this with 1.47 in place of the x by doing my last answer times 1.47 minus 1.5, close parenthesis, plus 14.13, 13.58. Excuse me. 13.578, but probably 13.58. And this would be a linear approximation of S, and S is in meters. We have a graph, and this is the graph of the derivative. It's kind of hard to see. That's the derivative. So if I'm going to do the second derivative, I want to use the slope of this on here. So this slope is almost zero. It's slightly positive, and it gets more and more positive till minus 1. At 1, it's almost 1. So it's pretty small, and it works its way up to 1. And then it works its way back close to 0. Not a very exciting graph. Not very much to it. And now if we're doing the function, that means the height of this graph is telling us the slope here. So the height is minus 3. So I have to start with a slope of minus 3. So I'm probably going to start up here. That's minus 3. And it kind of slowly drifts to a slope of 0 by here. So it's going -3, and it's getting less and less minus until it reaches a slope of 0 at -1. It's kind of a guess on where that would be in shape to there. Stays close to -3 for a while, and then it kind of slowly goes back to 0 and in the last few units. And then it goes to positive and then gets as steep as +3. So it's probably going something like this. There's a slope of about +3 there. And this could be up or down from that, but that's roughly the idea of this graph. Page 2. Find the equation of the tangent line to this at 2. So f prime of x, to get the slope, is 6x minus 2. So f prime at 2, the slope at 2 would be 12 minus 2, which is 10. So the tangent line at 2 is the slope at 2, x minus 2, plus the height at 2. So I need to find f of 2. 2 in here is 4 times 3 is 12. Minus 2 times 2 is 4, so that's 8. Use this limit definition to determine f prime at 0.5 on f at x to the x. So we're going to have to go the limit as h approaches 0 of a plus h to the a plus h, because we're going to use a plus h for the x, minus a to the a, because that's what f of a would be, putting a in for the x's, over h. So we got this. And we're supposed to find it at 0.5. So for all the a's, I'm going to put in 0.5. So doing this at a equal 0.5, I'm going to get the limit as h gets close to 0 of 0.5 plus h to the 0.5 plus h minus 0.5 to the 0.5 over h. And now to use technology to find out what happens when h gets close to 0. So I'm going to go to here and type in parenthesis. Let's start off with a fraction on here. I want to have parenthesis 0.5 plus, and I need a variable here, so I'm going to use x, close parenthesis, to the 0.5 plus x, using x for h, minus 0.5 to the 0.5, and then the denominator is just the x. And then I'm going to go to my table. I'm in ask on the table set, so I'm going to go to the table, get rid of these, and I want to get h close to 0. And I'm getting about 2.17, 2.17 or 16 is what this works out to be. The position of a bob of a pendulum, so the pendulum has a bob on it and it swings back and forth, is given by this equation. So its position at time t is 3 cosine pi t. And the position is in centimeters and t is in seconds. So this is centimeters and t is in seconds. What is the velocity at 0.5 seconds? Well, if this is the position, the derivative of position is the velocity. So that's going to be, let's see, derivative of the inside is pi times the 3 that's going to hang around, and the derivative of cosine is negative sine of whatever was in the inside. So that's negative 3 pi sine of pi t. And we're supposed to find the velocity at 0.5 seconds. So we get negative 3 pi sine of 0.5 times pi. And that works out to be negative 3 pi sine of pi over 2. .5 pi. And make sure I'm in radians. So I get the velocity is negative 9.4245 centimeters per second. Got to differentiate this. This looks like a quotient rule. So I take the derivative of the numerator, which would be 2x plus 3 times the denominator minus the derivative of the denominator. So derivative of the inside is 2. Derivative of tangent of something is secant squared of the something times the numerator over the denominator squared. Find the derivative of this. Well, this looks like a product rule. So I got to do the derivative of the first. Let's rewrite this as x plus 1 to the 1/3 times sine of 2x. So the derivative of this is 1/3 x plus 1 to 1 less, which would make negative 2/3, times the second, plus the derivative of the second, so the derivative of the inside is 2, and derivative of sine is cosine of whatever was inside, times the first. And that's that one. Find the equation of the tangent line at 2, 2. So 2, 2 works in this. Derivative of y to the third, since we're doing it with respect to x, we have to do chain rule. Derivative of the inside is dy dx times 3y squared plus the derivative of x squared is 2x, and the variable is x, so I don't need to go dx dx, equals, we have a product, so I'm going to think of 3x and y. The derivative of 3x is 3 times the second, y, plus the derivative of the second, the derivative of y is dy dx times the first. I want to solve for dy dx. These are multiplied, and these are, so I'm going to bring this one over here. So I'm going to have 3y squared dy dx minus 3x dy dx, and I'm going to bring the 2x to the other side by subtracting 2x from both sides. I'm going to factor dy dx out of these. And then I'm going to divide by this quantity, and so dy dx equals 3y minus 2x divided by 3y squared minus 3x, and then define the derivative at the point 2, 2. I'm going to plug 2 in for the y and then 2 for the x, so I'm going to get 6 minus 4 over 12 minus 6, which is 2 over 6, or 1/3. That's the slope, so the equation of the tangent line is, and I'm doing this at x, or at the point 2, so it's going to be the slope at 2, which is 1/3 x minus 2 plus the y value at 2, which is also 2. There's the equation of the tangent line. Page 3 or 4, I don't know which one I'm on here. Water is being poured into an inverted conical tank. That's a cone upside down. The tank is 20 feet high and a diameter of 30 feet, so I'm going to just put the radius as 15 feet. And it's being poured into the tank at a rate of 3 cubic feet, that's volume, per minute. So that's change in volume for change in time. 3 feet cubed per minute. Do you see how the units match up? And determine the rate of change in height when the tank is 4 feet deep. So I need a function that relates the velocity to the height, or the volume to the height. Well, this relates the volume to the radius and the height. So somehow I've got to get down to just a single variable. Well, this is the height, and this is the radius, but it's going to be at some water level that's not all the way there. So this will actually be the height of the water, and this will be the radius. And I think we have similar triangles. So the small triangle, see, I want to solve, let's say I want to keep h in it. So I want to solve for r squared. So I want to solve for r. So I'm going to put r in the numerator. R is to h as 15 is to 20. Do you see the similar triangles? And they set up a ratio. So I multiply both sides by h, and I get r equals, see, that's 3/4 h, or 0.75 h, if you will. So my volume as a function of only h, which is what I wanted the relationship between the height and the volume, is 1/3 pi r, which is 0.75 h squared times the height. So, clean this up a little bit. See, the h squared times h is h to the third, 0.75 squared. Is that times pi divided by 3. And I get 0.5890 h cubed is the formula for the volume as a function of h. But I want to take the derivative with respect to time because I want rates. So the derivative of volume, derivative of v, is 1 dv dt. The derivative of this is 3 times this, 1.767 h squared dh dt. And then we're supposed to figure out the rate of change of the height. So we're trying to find this when the volume is changing by this. So I got to put 3 there times 1. So this is 3 equals 1.767. What's the h? Oh, 4 feet deep. So times 16, 4 squared, dh dt. So I got to take 3 divided by this and 16. So I'm going to take this number times 16, and then I've got to take 3 and divide it by that, and I get 0.1061. 0.106 is what dh dt. Now h is measured in feet, and time has been measured in minutes. So that's how fast the height is changing per minute, 1/10 of a foot per minute. All right, 10. Two positive numbers, x and y's, multiplied to be 6. So x times y equals 6. Let t be the total of twice the first. T is the total, so we got to add twice the first. Let's just call x the first. Plus the square of the second. So that would be y squared. Find the pair of xy that minimizes the total. So we want to minimize this. So I want to find the derivative, but I got to get this as a function of a single variable. So let's just make it x. We'll get t as a function of x. So it's 2x plus, let's see, y would be 6 over x, wouldn't it? If I divide both sides by x. So y squared would be 36 over x squared. And for derivative purposes, we'll move the x squared up. So it'd be 2x plus 36x to the negative 2. So t prime as a function of x would be 2 minus 72 x to the minus 3. And we're going to set this equal to 0. So now for the purposes of doing that, I'm going to move the x cubed to the denominator again, setting it equal to 0. Multiply everything by x cubed. Add 72 to both sides. Divide by 2. And take the cube root. And I get 3.3. That's going to be the x. And y is equal to 6 divided by x. So I'm going to take 6 divided by my answer. And I get 1.82. 3.302 rounded for x. And the second number is 1.817. Yeah. There's the two numbers where the first one doubled plus the second one squared would be the smallest possible. Determine the limit using L'Hopital's rule. So that means as x goes to 1, what's this numerator go to? Well, 1 squared minus 1 is 0. It goes to 0. And ln of 1 is 0. So they both go to 0. So I can take and try to do this limit. I can take the derivative of the numerator and the denominator. If they both go to 0 or both go to infinities, then I can take just the derivative of the numerator. That would be 2x. Take the derivative of just the denominator. That's 1 over x. And put 1 into this and see what happens. Well, this would be 2 over 1, which is 2. And that's the limit of this as x gets close to 1. Next page. Determine f prime of x. Well, that would be 27 x to the second plus the derivative of ln x is 1 over x. Determine f double prime. Well, that would be 54 x, and this is x to the minus 1, so if I take the derivative, it would be minus 1 over x squared. It would be minus x to the minus 2, which puts it in the denominator. So there's the second derivative, and there's the first derivative. It says now show how calculus is to determine local max and mins. We set this equal to 0 to find max and min, so 27x squared plus 1 over x equals 0. So I'll multiply by x clear through. Subtract 1 and divide by 27. And take the cube root. So x is equal to negative 1/3. That's the cube root of that. So that's either a max or min. I put that back in the original equation, I'll get the point, but that's the critical point. And is it a max or min? Well, we'll find out by putting into the second derivative negative 1/3. So that would be negative 1/3 times 54 is, see, a third of 54, 14. Negative 14 minus 1 over 1/3 squared is 1/9. So this is minus, so the whole thing is less than 0. If the second derivative is less than 0, it's concave down, so this is where a max is. And so the maximum point is negative 1/3, and the height is 9 times 1/3 cubed plus natural log of 1/3. Negative 0.765. 0.765. That's the point. That's the critical value, and it has to be a maximum because it's curved concave down. Show how to use calculus to find inflection points. We find inflection points by setting the second derivative equal to 0. So we go 54x minus 1 over x squared equal to 0. Multiply by everything by x squared, we get 54x cubed minus 1 equals 0. Add 1 divided by 54, we get x to the third is equal to 1 over 54. And so the critical, the inflection point happens at x equal the cube root of 1 over 54. We could simplify that, but we'll also just get a decimal value. 1 divided by 54 to the 1 divided by a third for the cube root, and it's 0.264, approximately 0.2645 rounded. And if I wanted the y part, I'd put that into the original equation and get the y part of the point. Determine the intervals where f of x is increasing or decreasing. Well, if the slope is 0 at negative 1/3, then it's got to be increasing or decreasing before that. And after that, it's got to be increasing or decreasing. Now we could graph it, but we can also use calculus by checking before to the left of negative 1/3, like at negative 1, the derivative at negative 1, the slope at negative 1. Negative 1 in here would be negative 27 minus 1, so that would be negative. So it's decreasing before there. The slope is negative. And probably increasing here, but we'll try something bigger than negative 1/3. That might be 0. So I'll find out the slope at 0 by putting 0. I can't put 0 in here. But let's see. Well, let's put in 1 then. 1 would be 27 plus 1 is 28. It's greater than 0, so it's increasing. Oh, and the function doesn't even exist for there. This function, ln of x, doesn't exist at negative 1/3, so there's no max. How did I put in negative 1/3 into this? I shouldn't have been able to do that. What did I do? I forgot to put in negative 1/3, so that was incorrect. It would have given me possible. There is no max. Sorry, no max because you can't do 1/3 and negative 1/3 into that. We got inflection points. Let's take a look at this graph just to know what we're doing here. 9x to the third plus ln of x graph. It only exists for the positives, and it kind of goes up. It's curved down and then curved up. It changes curvature at some place at 0.265, but there is no max on that graph. There is no min on that graph. Okay, determine the intervals where it's concaved up or concave down. Well, looking here, you can see it's concave down and then concave up. But to find that, it changes at 0.265, just a little over a quarter. So I could find f double prime of 0.1 and see whether it's positive or negative. So putting 0.1 into f double prime, I'll just type it in. 54x minus 1 divided by x x squared, and then go to my here, and I want to find out at 0.1, and I get the second derivative is negative, so it's concaved down on the interval negative 0 to 0.265, and then it's concaved up from 0.265 to infinity, and we can check that. Something bigger than 0.265 is 0.3, and notice we get a positive value for the curvature. Okay. Determine any places where f of x is not differentiable. Well, it's not differentiable from negative infinity. Well, specifically, it's not different from negative infinity up through 0. It's not differentiable because it doesn't even exist over there. Okay. And